Good evening and welcome to Team 3's final presentation on the Cohico Creek Sustainability Water Delivery System, part of Cal State LA's 2021 to 2022 Senior Capstone Projects, sponsored by AZTEC Engineering. My name is Sherman Alvarez and I'm going to be starting this presentation where we'll be presenting the research we've conducted and the designs we've created over the past 2 semesters. Here's an outline of the topics that we'll discuss over the next 30 minutes. We thought it would be useful to split up our presentation into 2 different sections coinciding with the work done over the 2 semesters. Phase 1, the conceptual study phase, includes all the work we did during the first semester of the project. This phase introduces our problem statement, the location of the project, and the methodology used to complete the project. The project demanded the use of multidisciplinary approach, so the research and constraints were split up into different branches of civil engineering. The research conducted and constraints we found allowed us to create multiple alternatives where we continually collaborated with our client to ultimately decide on one recommendation that meets their demands and solves their problem. This brings us to phase 2 on the right side, the preliminary design phase, which took place during the second semester. Once the recommendation was selected by our client, the design was further developed to our current improved design. This design includes all the engineering design considerations for each portion of the water system. Phase 2 concludes with our commitment to sustainability, the cost estimate, and finally the conclusion to this entire presentation. In the next slide, we'll introduce Phase 1.
Hello, my name is Caesar, and I'll be introducing Phase 1 of the project, the conceptual study phase. Shown here on the right are all the aspects of Phase 1 that Jeremy just went over. Before we continue, I would also like to point out the timeline we included on the bottom of each slide to mark where we are within Phase 1, as well as the entire project itself. AZTEC Engineering has partnered with us to design and construct a complete water system for use in a future mining project. The current water supplier cannot supply the necessary water demand for their daily operations, so they have secured rights to the primary water source in the area, Lake Matthews, a subsurface aquifer, but it currently provides more than enough water to meet their demands. Therefore, the goal of this project is to design a complete sustainable water system that collects, transports, and stores water before being utilized. This complete water system must include a well, pump, pipeline system, and an access road. In the next slide, we will focus on the project location.
My name is Dominic, and I'll concentrate on the location of our project. Our project is located in Cajalco Canyon, California, just west of the city of Corona. The map presented in this slide highlights the general location of the project in white. Within our project site, it's the location of the well, shown as a star, and the location of the delivery location of the water, the client's future mining site, shown as a triangle. Our design must include a pipeline to get the water from the well to the future project site. The area's primary water source, Lake Matthews, is shown on the map on the far right. We have also highlighted Cajalco Road, which is the road that our access road will stem from. In the next slide, I'll give an overview of the methodology used to complete the project. The methodology we use for this project is called the civil engineering design process, which is a cycle of the 8 distinct steps shown here. Now that we have defined the problem, the next steps were to conduct background research in all aspects of civil engineering. This research helped us to identify the constraints that we needed to avoid or design around, while brainstorming solutions. Once the solutions were made, we came up with more alternatives until we decided that we created the best alternative to meet all of our clients' requirements. If the alternative did not meet all of our clients' requirements, solutions would be brainstormed again. The final step of the civil engineering design process is to communicate our results to the client. I will now pass it off to Furman to introduce the research and constraints.
My name is Furman, and I'll be starting off our research and constraints section with our environmental research and non-technical constraints. As mentioned before, the scope of this project necessitated the use of a multidisciplinary approach encompassing all branches of civil engineering. Firstly, this project falls under the municipal codes of the City of Corona and Riverside County. To prevent as much damage and disruption to the construction and surrounding area, we will be following the guidelines laid forth by the EPA. We will also be in contact with the surrounding stakeholders in the area to try and coordinate a time that would disturb them the least. To ensure the safety of our crew, we will have Cal OSHA provide safety training, personal protective equipment, and other necessary certifications. Any other training required will be covered in the workshops our company will be providing. There are several protected species living within the construction area. If species such as the kangaroo rat are found during construction, we will contact the Riverside Corona Research Conservation District. We have also kept the native birds in mind, because they have their nesting season in this area during the winter. We will be limiting the construction during that time. For the sustainability of the project, we will use solar energy because of the location of the project provides ample area to collect it. This energy will be used to power any equipment that can be powered with electricity and meet any energy requirements for the facility after the construction as well. We will also try and avoid disrupting as much of the environment as we can. In the next slide, our geotechnical team will expand on their research and constraints.
My name is Brianna, and I will be summarizing our geotechnical research and its technical constraints. Our geotechnical team was responsible with determining soil parameters and behavior in the area. A geotechnical investigation is one of the first steps that must be done prior to the start of a project. We were provided with an investigation performed by Lake Matthews on June 12, 2018 by Leroy Crandall and Associates that determined that most of the material composition was loam and there was no confining layer in the area, which means that groundwater can flow freely across all the layers of soil. The location of this investigation is shown on the map on the right. The team was also given 2 boring logs provided by the client that provided enough information to determine properties needed for designs of foundations and retaining walls. The location of these boring logs is also shown on the map, labeled B1 and B2. The boring logs determined the depth to water to be 26 feet and the depth to bedrock to be 163 feet. The given reports and boring logs also provided the permeability of the soil and the friction angle of the soil. The transportation team is next to provide some insight on their research and constraints.
My name is Ricardo, and I'll be giving a summary for our transportation team's research and technical constraints. The County of Riverside's Transportation Department is a partner agency for the City of Corona and others around the area. County of Riverside standard identifies our road design as a rural road, which restricts our vehicle speed to a maximum of 25 miles per hour for their safety. To make this all possible, we must create a private easement which will grant our clients the right to cross or use another's property. This easement will also give access to our workers when maintenance of the well is required. Going into the road material, we follow the cross-section reference of County of Riverside Standard number 106/817. The surface grade we will be using is impermeable asphalt, which is most commonly used road throughout the U.S. Going down the list, we have our final grade, then have our base of small aggregate such as silica sand and gravel pieces. Through extensive research, we follow regulations for a slope of the road must be a 2% or a quarter inch of fall per horizontal foot of the road width. Our water resource team will now expand on their research.
My name is Benjamin, and I'll be presenting the Water Resources Team research and technical constraints. Data was retrieved from our monitoring wells located within the project site, as well as the boring logs that were provided to our geotechnical team. They indicated that a depth to water of 23 feet and a depth to bedrock of 167 feet. From this data, we were able to find the aquifer thickness to be 137 feet. This information assisted us in designing our wells as well as our pump stations. I will also be going over the research and constraints from our structural team in the next slide. Our structural team research constraints of seismic parameters and proximities of fault zones from our project site. The project location has a peak ground acceleration of 0.836 Gs, which is based on the design horizontal response spectrum using the structure's period, as seen in the graph below. The structure is categorized as non-essential, meaning in case of an earthquake, if the structure were to fail, it represents less of a hazard to human life. The soil is composed of a very dense soil and rock. Lastly, the site has a seismic design category E due to its proximity to the fault zones, specifically the San Andreas, San Jacinto, and Elsinore fault zones, meaning this site could be subjected to severe ground shaking in the case of a major earthquake. The structures and their foundations must be checked to see if they can withstand seismic forces. Fortunately, none of the fault lines pass through our project location, though it still should be taken into account considering that California is very earthquake prone. The research enabled us to brainstorm different solutions, which I will be showing in the following slide. So one of our alternatives that we came up with was the trucking method to deliver water from the well location to the mining facility. We included two alignments and our considerations during the trucking method. Our first alignment, as seen on the left, had us transport water from the well location up the hill and to a storage tank located at the bottom of the hill. Later, trucks would transport the water up the hill into the mining facility. Our second alignment, as seen on the right, was similar to our first alignment. Instead, this one had the storage tank located closer up on the hill. Later, trucks would transport the water in the same process as up to the mining facility. I'll now be going over our alternatives for our storage methods. Our alternatives for our storage method included an open pit reservoir, which would be lined with a non-permeable material. The development of these alternatives eventually led us to our final alternative for phase 1 of the project, which Jesus will be presenting in the following slide.
Thank you. Hello everybody, my name is Jesus. So out of the different alternatives, we recommended this 8-inch water pipe network. See the image on the right? This transports water from the well, represented by the star, to the storage tank location represented by the square, and from there it transports the water to the tank located in the mining site, represented by the circle. This design incorporated two pump stations, one by the water well and the other at the proposed storage tank, so that from the storage tank the water can reach the mining site. We also proposed a 24-foot wide two-way access road to give ample space for service trucks to get from the existing road to the bottom of the creek and provide maintenance to the well and pump station. Since the road is needed to reach the bottom of the creek and the pipe alignment will run underneath the road, we recommend to build this portion of the pipe alignment concurrently to save time and resources. All in all, we recommended this alternative because the trucking method has seen an increase in gas prices, constant upkeep of the roads will be needed, and there's a larger probability of human error. As far as the reservoir, it will also need constant maintenance and not to mention the chance of the water supply evaporating. Next slide. Now I will be continuing our presentation by transitioning into phase 2 of the project, the design phase. As with phase 1, we have included all of the contents for phase 2 on the right. I would also like to remind you all about our project timeline on the bottom of the slides to mark where we are in the presentation. Next slide, please. After further research, we decided to update our design by relocating the site of the proposed storage tank further up the hill, which is represented by the square. This tank will now be supplied with a 6-inch pipe alignment instead of an 8-inch. We implemented retaining walls to the proposed access road and eliminated the second proposed pump station. Also, we will be providing a new storage tank for the mining site represented by the circle. It was relocated about 200 feet to the left from its original location. Since the storage tank was relocated further up, the elevation increased, which will allow the water to reach the mining site tank using gravity. This eliminated the need of the second pump station. Our water resource team will further elaborate on this. The cross section on the left was created to help our geotechnical team determine the heights of the retaining walls along the road. The red line represents the existing grade while the blue represents the finished surface. According to Google Maps, there seems to be a dirt access road along the side of the hill that would provide access to the new location of the storage tank. This is represented by the dark line on the image to the right. Next slide, please. Provided here is a plan and profile of our proposed access road. The blue line work represents the proposed road, the red line represents the existing grade, and the pink represents the pipe run underneath the road. The green area also represents our cut of the existing grade. We decided to provide a minimum of 4 feet of cover for the pipe to prevent any damage. Since the road was straight graded to have even slopes throughout, the majority of the work will require cuts due to the steep terrain. Next slide. Continuing the plan and profile of the road, again, you can see the pipe running underneath the road and the area of cut. This view provides the largest cut needed. Our transportation team will later discuss the total volume displaced. Next slide. And lastly, here our proposed road will connect with the existing road. This portion of the road will require the least amount of cut. And now that we have outlined our improved design, we will now transition to our design considerations.
Hello everyone, my name is Sergio Chavez and we have now reached the portion of the presentation where we start talking about our engineering design considerations for each portion of the water system and access road shown here. In the next slide, I will start our design considerations with the SECA checklist. With many construction projects, environmental impacts are part of the process. The SECA checklist is something we use to really think about what environmental impacts this project can have and what we can do to mitigate these impacts. Starting with aesthetics, when constructing a road and implementing water tanks on a barren land, it is easy to scar the land and create eyesores. To mitigate these issues, we worked with the natural terrain to construct the road, minimizing the scarring. To add a pleasant view, we will be screening the water tanks with trees. In terms of housing and population, we know that construction brings lots of traffic to the area, so we will be implementing work schedules to minimize impacts to the local traffic during AM and PM peak hours. And we will also coordinate with the nearby residents and stakeholders as well. With any construction project, noise can also be an impact to surrounding areas. Therefore, we will also be scheduling work in accordance to Riverside County Ordinance 847, which allows work to be done for certain hours during certain months. I will now hand it over to Cesar to talk a little bit more about this SECA checklist.
My name is Cesar Ortiz, and I'll be continuing the SECA checklist sections with the following three categories, which are greenhouse gases, hazardous materials, and land use planning. Greenhouse gases emissions' biggest effects are for the climate and air quality. The two main greenhouse gases are methane and carbon dioxide, which trap heat within the Earth's surface. Our proposed mitigation for this category is to choose between a sustainable energy source. We chose to go with solar energy due to the high sunlight period in Cajalco Creek. Also, during construction, only Tier 4 equipment will be used to ensure that equipment engines running during construction are emitting the least amount of fossil fuels. To move on to the second category, which is hazardous materials, the project site location will be evaluated to ensure that there is no hazardous materials present from previous land usage. Lastly, land use planning is the third category, and there's going to be no impact on current or future use of land used to build our pipeline system and tank. The team will ensure that construction will not impact or interfere with current land uses such as access roads.
My name is Alexander, and I will be covering the categories of air quality, biological resources, and transportation under the SECA checklist. The Riverside Corona area is subjected to high wind speeds and is prone to wind erosion. To mitigate air pollution, our team would implement dust control practices such as water dampening and placing windbreak net fences around appropriate areas. In cases of extreme wind conditions, any dusty activities would have to be rescheduled. Proper aggregate coverings would be used to control particulate matter, and low-emission Tier 4 equipment should be used wherever applicable. This site is located around the Lake Matthews Mountain Reserve, and to help mitigate the disruption of wildlife, we should avoid construction during the nesting season, due to birds using the area for feeding and resting. Animals found on site should be relocated, and a protective barrier should be placed to deter them from entering the construction site. After project completion, the animals shall be reintroduced to the environment. We will also preserve the topsoil for reuse, due to its abundance of nutrients and organic material. This will help with the reintroduction of local flora and fauna, while leaving the site as natural as possible. Lastly, a traffic study shall be conducted to determine the best times to work as to not disturb the existing traffic flow. I will now pass it over to Jennifer to wrap up the SECA considerations.
My name is Jennifer, and I'll be wrapping up the environmental design considerations. I will discuss the four categories of the SECA checklist that did not possess significant impacts but were considered in our design considerations. The four categories are agricultural, forestry resources, public services, recreation, and service systems. Regarding agriculture, forestry, the land in Cajalco Creek is generally low in trees and is mostly desert land. Therefore, minimal disturbance for agriculture or construction will occur. As for public services and recreation, the project site location is private land and we have no intent of constructing any public system for public or recreational usage. The fourth and last category is service systems. The project does not propose the utilization of wastewater treatment facilities, as the water discharge will be filtered in the ground or diverted to the creek and used for dust control. This concludes the CEQA checklist to assure the proper mitigations are proceed to assure the least environmental impact. Now that we have finished going through the CEQA checklist, we can proceed with our other engineering design considerations.
My name is Adolfo, and I want to quickly go over our pipe alignment again before continuing with our design considerations. To have an idea how things will perform, we can refer to the image to the right, representing our project's pipe alignment. This AutoCAD image demonstrates how we will transport the water from our supply, which is the well, to our clients. The water supplied is pumped from our well located at the start, and travels through our pipe as seen by the purple line, and into our storage tank indicated as a yellow square, and into an existing tank indicated by a yellow circle. The well is located at boring log B1, which provides us with information of the unconfined aquifer. Now we can move forward with more of our engineering design considerations, continuing with the well design. The required yield is 500 gallons per minute, which translates to 1.114 CFS. The soil permeability according to the boring logs is 2 gallons per minute per foot. We use a steady state condition and use the drawdown equation, expected for small drawdowns, for an unconfined aquifer to determine all the parameters of our well. We determine the diameter of our well to be 8 inches or 0.67 feet with a depth of 137 feet. We will be utilizing a pipe-based wire wrap screens as they are best in performance and are cost effective for extracting water. We will use fine gravel and coarse sand to surround the well and filter the water entering the well for our filter pack. Our upper section of the well consists of bentonite clay and cement grout to prevent surface water from contaminating the pump water. The well will not require a pump as there is enough atmospheric pressure to allow water to rise. Finally, to establish our well, the drilling method will be a rotary method. Now that we have gone through the well design, we can transition into our pump and pipe calculations.
Hello, my name is Moises and I will be responsible for the pump and pump station. In order to be able to select a pump that can pump water from our well into our proposed storage tank, we need to calculate for our pump head loss. For that, we use the energy equation and the continuity equation shown below. From the continuity equation, we get a flow velocity of 5.6 feet per second using a 6-inch diameter pipe. From the energy equation, we were able to calculate a total pump head loss of 411 feet. The pump that was selected was the model SC43C10 by Pioneer Pumps, which has a max head of 490 feet and a max pumping rate of 800 gallons per minute. By graphing our system curve and displaying it on top of our pump's performance curve, we can see that at a rate of 500 gallons per minute, the pump will run at a 69% efficiency and will require a motor of 75 horsepower. Moving on to our pump house. Our pump house will be a galvanized steel shed-like structure, which will be 10 foot wide, 20 foot long, and 11 foot tall. The pump house will be located next to the well at the end of our proposed access road shown at the image on the bottom left. The structure will house our one main pump that will be running at all times, one backup pump in case of maintenance, as well as any other utilities that are necessary to keep the pumps operational. The next slide will discuss the pipe selection.
My name is Carlos Lupercio and I will be going over our pipe selection. As previously stated by Adolfo, the first section of the pipe, which travels from the well to the storage tank, will be a length of 3,372 feet. As for the second section of the pipe that travels from the storage tank to the mining facility, it will be a length of 992 feet. As mentioned before, the pipe will be 6 inches in diameter with a flow velocity of 5.6 feet per second. We utilize Bernoulli's equations to determine the parameter of the pipe. The material will be a ductile iron pipe due to its high strength and long service life. The pipe will be cement lined, which will prevent any water corrosion
from the interior of the pipe. The pipe will be installed 4 feet underground. Additionally, it will be installed in a Type 3 trench for additional protection against external loadings such as maintenance trucks, which signifies that we will have a 4-inch minimum bedding, a highly consolidated backfill to the top of the pipe, and our total cut will be approximately 2,000 cubic yards, more precisely 1,951.6 cubic yards. In the next slide, I will continue to talk about tank sizing. The Ribble method was used to determine our tank storage. The pump will function at a rate of 500 gallons per minute from Monday through Friday at 8 hours a day, while Saturday through Sunday it will pump for 5 hours a day. In knowing the rate of the pump, we can analyze our cumulative demand and cumulative supply, as shown on the graph to the right. The gap indication will determine our required storage amount. The difference between the supply and demand resulted in 314,700 gallons, about half the volume of an Olympic-sized swimming pool. This value enables us to professionally design an appropriate sized tank. As we have mentioned before, our design includes 2 water tanks, a storage tank, and the mining site tank. The mining site tank will be discussed in the next slide.
My name is Jonathan Alvarado, and here we have provided the client with the new tank that sits on an elevated truss taller than their trucks for easy refilling. Since our storage tank is at a higher elevation, water can be delivered using gravity. Unlike a pump where a constant flow rate is achieved, using gravity will result in a range of flow rates. Therefore, a control valve will be installed so the employees can control the rate in which the water is delivered from the storage tank into their mining site tank. The complete design of both tanks will be presented in the next slide. I will be discussing the 2 storage tank designs. The tank design was based on the following standards: the American Society of Civil Engineers, ASCE 7-16, and the American Water Works Association, AWWA D100-11. The material is composed of ASTM 836 steel. Structural analysis was conducted via SAP 2000 software, which models to apply the seismic weights for a flat bottom tank. The storage tank has a diameter of 48 feet, a height of 24 feet, a capacity of 315,000 gallons, and a thickness of half an inch. The mining site tank has a diameter of 12 feet, a height of 10 feet, a capacity of 8,460 gallons, and a quarter inch of thickness. The anchor design for both tanks will be discussed in the next slide.
My name is Mach, and I will be responsible for the anchor design for both tanks. The anchor bolt design was referenced from the Simpsons strong tie anchor designer software, following the American Concrete Institute Standards ACI 318-14. Information provided by the SAP 2000 analysis for both tank designs. We used the maximum uplift and shear force, which calculated the best overturning and sliding resistance. The storage trunk will require both diameter of 1 1/2 inch with a plate thickness of 3/4 inch for every 1 foot spacing. A total of 145 heavy hex bolts are needed to support the storage tank. The mining site tank will require a bolt diameter of 1/2 inch with a plate thickness of 1 inch for every truss corner. A total of 16 heavy hex bolts are needed to support the truss. The foundation design will be presented in the next slide.
My name is Alexis, and I'll be summarizing how our geotechnical team was able to design and size the foundations for our 3 structures: the storage tank, mining site tank, and the pump house, which are located on the right side of the slide. Since the bedrock is very deep at our project location, and the aforementioned geotechnical investigation and boring logs do not indicate unstable soil layers, shallow foundations made out of concrete were deemed appropriate. The foundation type and shape is different for each of the 3 structures to cater to their specific loads, shapes, and supplemental structures. Using information from the boring logs, the geotechnical team was able to calculate the bearing capacity, which is the capacity of the soil to support loads applied to the ground of the soil. The nominal bearing capacity of each structure is dependent on its load, which was provided by our water resources and structural teams. The allowable bearing capacity was calculated using Vesic's formula, which contains factors that account for shape, depth, and inclination of the foundations. Following the AZTEC method, the allowable bearing capacity was divided by our initial factor of safety of 3 to check if the chosen proportions of the foundations were bigger than the nominal bearing capacity. If so, the foundation was further checked for overturning, sliding, eccentricity, and seismic forces. The final specifications for all 3 foundations will be presented in the following slide.
My name is Juan, and I'll begin with our designs of the foundations for our storage tank, then our mining site tank, before concluding with our pump house foundation. The storage tank is our largest structure, so its load is also the largest, necessitating the need for the largest foundation. We used a circular slab-on-grade foundation for this structure to match the overall shape of the tank. Our calculations, as well as our safety checks, produced a circular foundation at a depth of 6 feet and a diameter of 65 feet. The mining site tank had the second highest loading, but its foundation is a little different from the storage tank foundation. As we have previously shown, the mining site tank is supported on a truss, so its foundation type had to be changed to a mat type foundation to support the 4 corners of the truss. We ended up with a square mat type foundation at a depth of 3 feet and a width of 15 feet. Our last structure, the pump house, had the lowest loading, which met all safety factors with a square foundation at a depth of 0.5 feet and a width of 10 feet. Overall, the seismic forces governed our equations, causing the foundations of the structures with the larger loadings, such as the 2 tanks, to be larger than the structures themselves. This also caused our final factor of safety for each structure to be larger than our initial factor of safety of 3. Next, the final design considerations for the access road and its retaining wall would be outlined.
My name is Walter, and I'll be going into depth about the access road design. It will be a 2-way road with a total length of 1,152 feet long and 24 feet wide. After months of research, we have concluded to use impermeable asphalt. Impermeable asphalt will not allow water to penetrate, therefore forcing it to run off. It will be a 1/4 foot deep and a total area of 6,912 square feet. For the middle layer, we will be using a base, which will consist of uncrushed gravel, coarse aggregate, chippings, and natural sand. It will be 1/2 foot deep with a total area of 13,824 square feet. We will be using a compacted subgrade for the bottom layer, and it will consist of soil. It will be a 1/4 foot deep and with a total area of 6,912 square feet. The total cut amount was about 481.22 cubic yards, and for the fill, it was about 19.75 cubic yard, which will only be needed for the first 75 feet of the road. After the cut and fill, the slope of the road will be 13.75%, which fits the regulations for maximum slope.
The retaining wall was required to reduce oil soil excavation and provide roadway from the pump house in the main roadway. For following Caltrans standards, the retaining wall will consider horizontal seismic coefficient, peak ground acceleration, passive and active pressure, soil density, and angle friction. The team concluded that a left and right retaining wall with multiple heights will be needed for the road. As shown in the right, the height of the left retaining walls are 17 feet, 27 feet, and 37 feet, and the right retaining walls are 5 feet, 10 feet, and 24 feet. The following factors of safety for overturning, bearing, and sliding have been checked and passed the liable requirements needed. This concludes all of our engineering design considerations for our completed water system. In the next slide, we will be going over our commitment to sustainability.
As we have mentioned continuously throughout this presentation, we have designed our complete water system with sustainability in mind. The SECA checklist helps us view what environmental impacts this project can have, and we have mitigated these impacts as much as possible. Just to recap a few in terms of aesthetics, earthwork removal was minimized to conserve the environment and minimize scarring of the hillside. The water tanks that are essential to this project will be visually screened by trees, so they cannot be seen. Air quality, during construction will be controlled via dust control and additional landscaping after construction. The biological resources in the area, which include endangered species and nutrient-rich topsoil, will be preserved or moved during construction and reintroduced once the project has been completed. Lastly, the use of Tier 4 equipment as well as scheduling work hours will minimize greenhouse gas emissions. The implementation of solar panels will also make our project more sustainable. We have opted to install ground mount units near the storage tank for optimal performance. The solar energy will be stored in a power pack and used to power our pumps. With peak sun hours averaging around 5.8 hours in Riverside County and the units being at the top of the hill, these systems should be effective for our use, and in turn savings will improve the salvage value of this project.
My name is Alex and I will be discussing the cost of the project. The total cost of the project is about 18 million. The calculation involved conducting a classified order of magnitude. The costs include pipe, tank, road, and well costs, among others, are shown on the chart in millions. The sum of those costs was used to calculate an additional 30% of contingency, 15% environmental and mitigation, 9% construction, and 8% engineering costs. The total cost for the project might be inconsistent due to the pandemic and the effect on inflation. In the next slide, I will be discussing over a cash flow analysis of the project. A cash flow analysis helps us analyze the total expense our client will pay for this project over their 50 service life. The annual expense include the electricity cost of $950,000 and 8% maintenance cost based on the construction cost of the project of $870,000. Though electrical costs could be lower if the pump are run before and after the peak hour using the renewable energy. Assuming a 1% interest rate and giving the pump having a service life of 11 years, the pipeline service life of 50 to 100 years, the water tank a service life of 30 years, and a road service life of 20 years. We estimate that our client can expect a total annual expense of $2.39 million. And now I will pass it on to Beatrice.
My name is Beatrice and I'll be concluding our presentation. AZTEC Engineering partnered with us because their water supply was greater than their demand. Through 2 semesters of research, design, and analysis, our group was able to meet all of AZTEC Engineering demands by designing a water system. We believe that our design is the best solution to our client's problem because it is sustainable, environmental friendly, cost-effective, and integrates into the natural environment without interfering with existing utility roads and structures. We would like to thank AZTEC Engineering and Cast.LA for giving us this opportunity, as well as the audience for coming and giving us your attention. If there are any questions, we would be pleased to answer them. Thank you.